player in reinforcement learning. Yeah, this is the paper. This is a Q, in case you read the paper. The authors are from Belgium. They published in Neurocomputing in 2009. Okay, so this is our setting, reinforcement learning. Here are agents. We have a control, we interact with the system. We receive rewards. Okay, we can propose a model for the system we are interacting with. And we have an opponent. This is two-player reinforcement learning. The game is zero-sum. That means that our reward is the opposite of the opponent's reward. Also, we can model the opponent as a black box in the sense that we not necessarily know about the policies and the state of the other opponent. And this motivates a slide about this guy, an ancient Greek guy, which basically talked about the fact that we can only know things about ourselves, not about the environment. It's not actually my quote, but the quote of Littman. This is not our paper, this is another paper, Littman, 94. He makes a review of the formalization of reinforcement learning. We will go one by one. The first one is, for the first scenario, we can formalize it. And adaptive agents, ourselves, we're interacting with the environment. I would model for this once then the Markov decision processes. We saw this example in class. This is a simplification from, being a PhD student, a full-time professor, dying. So, okay, then he says, in these points of view, solipsistic, we only know about yourselves. Secondary agents can only be part of the environment, that is the conclusion. So, the framework for two agents in reinforcement learning is Markov games. Okay? He introduces this framework, and Littman in 94 proposes a variation of the typical Q-learning algorithm called minimax Q-learning. So this is important. Our paper does the same and builds upon this base. Okay? This is a quick review of previous works. Just that this is our paper. This is the paper it is based on, Littman 94. And this is the deep learning revolution, where you see deep and the same, but with the word deep. So they actually quote this other paper, and they use this as a benchmark. So this is our problem. We are learning online. That means we play, we learn, we play, we learn constantly. And this is a loop. It's the main part of the online learning algorithm. Basically, we choose an action. We get, our actions have consequences. We learn from them, and our state is updated. This is very general. It doesn't assume synchronicity. It's not a model for information, and it allows us to include noise. But this is the point of the paper, just changing the learning phase. So they propose this algorithm called QL2 and QL2+. This is the one by Littman, I mentioned before, minimax Q-learning. And these are two vanilla typical algorithms in the literature. So okay, these are algorithms. A very quick mathematical framework to introduce their algorithm. You recall the motivation in class about the discount rate. We have money now, money tomorrow. That is multiplied by some rate, the compound rate model. So we have this formula over here. And this is the cost of time while we Then we have another mathematical object we will use, that is, for example, walking on a grid. You don't want to fall, and you have policies. So I can go to the right, to the left. The policies are these four numbers, okay? You have four policies at each point, so they're state dependent, depend on each point. Policies, this is the agent's policies and the opponent's policies, okay? And finally, we have the environment itself. This is not the great example. The example of the professors was better, but this is the case of a probability transition function, And here, what can I go to the right now? An example. So this is the core of the mathematical model. This is the expected return, as its name indicates, what we are expecting to get as a return. And there is the implementation uses this so-called evaluation function. I will call it Q. And this is the point. We can recover the expected return by introducing a more general Q and marginalizing over our own actions and the opponent's actions. The point of this is just introducing a recurrence relationship using Q to get then the formal solution via the so-called Bellman equations for this problem. So this is the problem. And all the different algorithms differ on how you solve it. So we have Q-learning, that is a way of solving it. In particular, we're interested in the policies we learn from it. Then there is minimax Q learning by Littman. We are comparing against this paper, the old paper from '94. In particular, look at this. To get the policies, we have to solve a linear problem at each step in time. You're learning online, so at each time you make a move and you solve a linear problem. You make a move and you solve a linear problem. The authors introduced this, not this is the Lagrangian of the Bellman equation. But they introduced to solve this problem, because the Lagrangian requires checking the minimum of Q, and this is not differentiable, so they soften it by changing the minimum operator by this that they call softmax. So yeah, they smooth it a little bit, and they perform gradient descent. Before that, they include a parameterization for the policies also. This is the typical in machine learning, they call it softmax there. This is a trade-off, how much do you smooth it? There is a special case for how much do you smooth it. It's the QL2 plus, we have QL2 and QL2 plus. QL2 plus is a special case of the limit of minus infinity for the parameter, which in physics they associated with the zero temperature version. This is the algorithm. We won't see it in detail, this is the last part. Just their point is different. You're not solving a linear problem, you're performing gradient descent. Parameter update. Okay. The results are presented based on this model. This is very self-explanatory. We have two agents playing football here, it's pretty self-explanatory. And these are the results. They play against an opponent, a smart opponent, and they have some conclusions. Okay? Minimax Q, again, the paper from Littman '94, this is our benchmark. And QL2 and QL2 plus, the conclusion is this one. They have the same convergence speed, high is good, it's a good result. So in the same number of epochs, they achieve the same good results, but they say they do it with less sequential computational time. Okay? They have this number, and the other one was much slower. That's the conclusion. There is a table you can go to check some heuristics about these algorithms. Then this is our implementation. So we are this agent over here, and this is our opponent. These are our goals. So two random players. This is a numerical simulation. I don't know if I have time for this. I'll go really fast. They can move randomly. They are random players. Eventually, they make a goal. Okay, they score a goal. This is not correct. This is just how much they are winning the cumulative reward. And you can see none of them is clearly winning. Sometimes the blue one wins, sometimes the red one. We can, of course, introduce some hard-coded algorithm to play football. And the hard-coded algorithm, this is red, wins very consistently, wins, and accumulates a lot of winning. It's very simple. You just go in the right direction and wiggle vertically a little bit. So we're almost there. We make a goal. Okay. Again, he starts with the ball. He moves. Okay, that was not good. We start here. We go forward. Well, and again, this is not going fast, but I will just go to the last part of it. That's not part of the time. And well, you eventually make a goal. Okay? So it's a smart agent and a random agent. The point is, now I implemented Q learning, not the other two algorithms, but it's the same. If you want to do it, it's like you only need a Q and a pi, a policy. So you need two matrices, two containers, and you have an update rule. It's pretty simple. You just iterate. Okay? So you have some parameters, the reward, and there is a trade-off here, interesting, like concepts that are part of the paper, and we can translate back to this special implementation. You have a convex sum, no? You have the parameter alpha, and you have your update for Q is a little bit about your past, how you were before, and some learning term. Just some more intuition. You can leave alpha as 1, you can keep learning if your opponent is deterministic, but if not, you eventually decrease it to stop learning, because your environment is random. So with this algorithm, we beat the random player. Pretty simple. We are the red one. We keep increasing. We increase the parameter alpha to stop learning eventually. And you recall, not having a cost for time implies unbounded gains, right? Your discount factor does not discount. This is another metric. We don't have time for this, just in black. What percentage of the games are we winning? A lot. Yet more metrics. just a relevant concept behind this, not time for this metric, just the difference between the first and the second maximum for Q. In this case is important because the policy is it's a pure policy, not a mixed policy. You are taking the argument maximizer, so you care about the maximum being unique. Some cases of bad convergence will show a non-unique maximum. So you're happy because this is different from 0. Well, just to show, okay, we're winning the random environment, but our strategy is not clearly optimal. It's just a local minimum, I call it, a blinker. You move down, you move up, you move down, you move up. And this is how you win, doing only that movement. Not optimal. So no more time for our case, it's just you include time costs and suddenly the reward is bounded. Again, we win. And now we play against the random environment, the smart environment, and again, we win. So yeah, Q-learning was very powerful in these terms, but there was one thing funny about this before ending, that was the following. Actually, we were performing better with Q-learning, playing against the smart environment, 600, than against the random environment, 80. These are values of reward. In particular, we won 80% of the time against the smart agent, and only 60% of the time against the random environment. So one last question is a fully deterministic opponent even more destructible? Well, this is the fully deterministic opponent. He just walks to the left or to the right, no wiggle, no random vertical wiggle. And the question was, no, actually we performed very poorly. Actually we lost a lot. We only win 20% of the time here in black. And the maximum is not unique. So this sums up my presentation, just to mention the last trade-off, which was, again, some randomness was okay, too much randomness was okay, but we didn't perform as good because you can only beat the average, and the average imposes some performance. And then no randomness at all was very poor. So just back to the paper, the last result is, now that we introduce this new metric of how much we win, how much we lose, how much we tie, you tie 0, 0. So they have Liebman's algorithm, minimax Q, and their own algorithm, QL2, QL2 plus. They perform equally well, they win as often, they lose as often, but their algorithm is faster. So that wraps it up, just proposing looking at Messi and thinking of an array of policies. So thank you very much.